This is the first in a series of lectures covering the topic of chemistry. Now, in order to discuss chemistry, the first thing that we need to know what is chemistry. Now, a difficulty whenever you're starting a subject is that you don't have any fundamentals laid out yet, so it can be difficult to answer questions like these. So we're going to have to come in with some assumptions. We have some ideas of phenomena that we would like to describe, and we come up with this somewhat naive definition, but it covers all our bases. We're going to call it the study of stuff. That's the common thread to all the questions that we're asking. There's always some stuff involved. Now, this is a perfectly adequate definition that we could continue to use, even up into the more advanced forms of chemistry. But as a scientist, we usually prefer a different term for stuff. We call it matter. It means identically the same thing. But that's more common in our parlance to call it matter. Now, so that's what chemistry is. What's our next question? Well, our next question, if we were a petulant child, what are they going to ask? They're going to ask us, what is stuff? And probably continue asking questions like that, which are going to get us in trouble because we quickly find out that we lack the ability to answer these kinds of questions. And actually, we have already reached that point. We've already reached the point where we can't adequately answer this question. In fact, our answer is going to be, this is too complicated. Now, that's perfectly reasonable in science. In fact, this is the really interesting part of science. So if we already knew everything, no one would do science. Science would be a dead field. Science is interested in where we don't have the answers. And so we've already reached that point. We don't have the capability to answer this question yet of what stuff is. But that's okay. Since we can't answer that question, we can do something almost as good. We can write down some of the information that we do know. And this is what we do know about stuff. We do know that it seems to have some consistent properties. Things don't tend to wildly vacillate in their characteristics. We also know that things are made of stuff. And, as far as consistent properties go, we could even try and start pinning some of those down. So maybe it seems like stuff always has volume and stuff always has mass. Now, is that going to be true in every instance? You can ask the physicists who are searching the galaxies for dark matter. But this is going to, I think, be pretty true for us. Okay, so now we know a little bit about chemistry, and we know a little bit about what we're studying. But in order to get further, I think we're going to have to ask the question, how? How can we study this stuff? Well, there are various strategies that we could try here. One thing we could do is we could just kind of sit down and reason about it and think of what seemed to be likely to be true. And that's what the original scientists / philosophers like Aristotle did. They just thought about it, and they came up with lots of answers, and those answers turned out to be wildly incorrect. There's a better way, which is more recent, and this is called the scientific method. That's going to be our go-to for answering questions about stuff. There are a few different formulations of the scientific method. One common formulation, which is the one that we will stick with, is that, first of all, you start by posing a question. Why would you be trying to obtain information if you didn't have a question? So this is sort of justifying our research here. Okay, so now we have a question, and we are going to go ahead and speculate on an answer. This is okay. It will maybe not be correct, but we're going to tentatively accept it as being possible, and we're going to call this a hypothesis. The next thing that we need to do is we need to test that answer, and the way we do that in science is by performing an experiment. Now, after we perform the experiment, this experiment is going to have some sort of outcome. And so what we are going to do is we are going to analyze that result. And this will provide us with some additional information that we didn't have before, if only confirming that we don't know anything. Now, this process leads to a few things. One of the things that it leads to is observations. And so observations are the points of data that we collect during our experiment. And so, for example, maybe we took some cesium and we added it to water, and there was a reaction. And so that was our observation. There was a reaction when we combined these. Now, in addition to observations, we have what are called laws. And so what a law is a concise summary of many of these observations. So an example of a law, we might observe over the series of a course of experiments that whenever we have heavy objects, that there's always a force between them, that they always attract. And so that would be our law of gravity. Heavy objects always attract. And so that summarizes all these different experiments that we performed, where we had skyscrapers and we had kettlebells and we had elephants, and we were able to measure this attraction in each of those cases. Compare that to an observation, which would just represent an individual case. Now, another way that we could represent this is mathematically. And so, for instance, Newton came up with this relationship, that this gravitational force was equal to a constant times the product of the masses of the objects divided by the distance between them squared. And so this is another way of writing a law. This summarizes the amount of attraction in each of these cases. It doesn't actually tell us anything. It doesn't explain why that attraction exists. It doesn't explain what gravity is or why it should exist. But for any experiment that we might perform, it gives us a piece of information which is consistent between those experiments. Now, something a little bit more ambitious is once we come up with what's called a theory. So a theory actually does attempt to explain a scientific result. And so it might, to build on our previous example, it might say that the reason that heavy objects attract is because they bend the curvature of space. So now we have a rationalization for why this should be true. Let me go ahead and show you. Here's a picture of that. And so this curved grid here that represents space and time combined together. And you can see there's kind of a indentation where the Earth is. And so the moon is trying to travel in a straight line, which it would do if this was perfectly flat, but since it's curved, that actually means that it winds up moving around in a circle. You know, just like if you were trying to roll a ball along a surface like this that had been curved. And so that's what leads to the force of gravity. And so this explains why gravity would exist, why it would be present. And that's the nature of theories. Laws, they summarize things. They don't give you an explanation. Theories, they do give you an explanation. And the nice thing about a theory is that it leads the way to new experiments because it will often have implications not present in the original data. So, for example, one implication would be, all right, so regardless of whether something would have mass or not, it would still be deflected by this curvature, right? Anything trying to move in a straight line here is going to be deflected. And so something that doesn't have mass, like light, would also be deflected. You have a beam of light coming in here. It will wind up moving in a different direction because of this curvature. And so an experiment was conducted to see if this actually occurred, and it turned out it did. So this helped to validate Einstein's theory of general relativity. Now, what if there was some other reason that light bent like this? Well, that's one of the limitations of theories, is that they give you an explanation, but you don't necessarily know that it's a definitive one. So let's see just a few examples of this. Try and classify these statements according to our definitions of observations and laws and theories. First statement we'll consider, black holes are wormholes to other dimensions. Well, this is a general statement, refers to lots of different black holes. Black holes have different sizes, different locations, some different characteristics. And so it's not the same situation every single time. So this can't be an observation, which would come from a single experiment. It must be either a law or a theory. So how do we distinguish between those? Well, a theory gives an explanation, and that's what this does. It explains black holes as being wormholes to other dimensions. This isn't observational information, so we haven't actually gone to these black holes and determined they connect to other dimensions. Just trying to explain, why they exist and why they're there. And so this must be a theory. All right, next statement here says the sun is comprised of hydrogen gas. Well, our clue is that we could figure this out simply by looking up at the sun with our spectrograph and seeing that it was made out of hydrogen. This is something we can establish from a single piece of data, a single experiment. That means that it is an observation. Finally, we have the speed at which galaxies are moving away from our galaxy is proportional to their distance. So again, this is a general idea. It refers to different galaxies and different orientations. Some have nebula, some have different star systems, and this describes all of them. So it can't be an observation. It has to either be a law or a theory. All right, well, what's it saying? It's saying that there's this constant ratio as far as the velocity of the galaxies compared to their distance. So really, this is just a mathematical equation. And so it's not a theory. It doesn't give any explanation. It doesn't say why the galaxies are moving away. It doesn't say why this is proportional to their distance. It doesn't explain anything. All it establishes is this constant mathematical relationship. And so it just summarizes a bunch of experiments that have been performed, and in every case it turned out that this ratio was observed. And so that makes this a law. Okay, so scientific method is a very wonderful tool for finding out empirical truth, and it's going to be our go-to in chemistry and other sciences. But there's no such thing as a good thing without any cost associated with it. And so there are some caveats to using the scientific method. One caveat is that we have the problem of bias. And a way that bias comes in is that it's scientists who choose the questions to ask, that first step in the scientific method. And because they're choosing it, they're going to bring in their human preferences. And what happens if they never ask the right question to, explain the fundamental meaning of the universe? Well, in that case, we're not going to ever find the answer to that question. And this is also good in a sense that we have bias. We usually bias ourselves towards productive experiments, right? We're not going to keep dropping a rock and then drop an elephant and then drop a giraffe and test every object in the universe to see that gravity applies. However, we might, because of our bias here, miss out on asking the questions that we need to ask. So it's a double-edged sword here. Same thing for our hypotheses that we come up with to answer these questions. If we don't come up with the correct answer to test, then the scientific method is not going to yield that answer as a result. And so maybe human brains are just not wired to ask the question that would explain all the physical laws or posit the answer that would explain all the physical laws. And so in that case, we would never find out that explanation as human beings. And that's just something we'd be stuck with. Another limitation is that we can only ask certain kinds of questions. So science is descriptive. We describe phenomena. We can't use it to answer questions about what ought to be. We can't answer, should people do this, or is this moral, or is this just? Those are the kinds of questions that might have correct answers, but science could not give us those answers. We also, even when we come up with our answers, we can't prove them, can't prove our explanations. The best we can do is show that for all the experiments that we've performed, there's no contradictions so far. But there would always be alternate explanations that we could come up with. And so usually we choose the simplest explanation as the one that we use to model our knowledge. But who's to say the simplest explanation is the correct one? It could be that gravity actually comes from fairies pushing objects around in the universe. And if those fairies don't manifest any other physical attributes, they just cause the sense of gravity, then we would never be able to know for sure. Another issue is once we get to the third step of performing our experiment, we might have an error in that experiment. There might be some random fluctuation which caused us to get a result we wouldn't normally get, or we might have made a mistake in our setup for how we thought that it was going to work. And in that case, we're going to incorrectly prove or refute the hypothesis that we came up with. And so the best thing that we can do is perform more experiments, and that will make us more confident, but it will never completely guarantee the answer that we've come up with. Now, it's actually very important that we keep these limitations of the scientific method in mind. And the reason for that is if we use a scientific method improperly, that's going to give us bad science. Now, as an example, in 2012, the pharmaceutical company Amgen decided that they were going to try and reproduce a bunch of seminal studies in cancer research because they're trying to find anti-cancer drugs. And so they want to make sure that the groundwork that they've laid for doing this is all solid. And so their 2012 study, they analyzed 53 seminal research papers. And want to go ahead and guess how many of these experiments they were able to reproduce? If you guessed more than 6, it was too much. They were able to reproduce 6 out of 53 of these papers, these landmark studies in cancer research. Now, it might not be necessarily that these remaining 47 studies were all incorrect. It could have been that Amgen, in the course of attempting to reproduce them, made some errors. I'm sure that's what the scientists would claim. But probably, there's at least some significant fraction of those 47 papers which actually legitimately were incorrect. Why does this happen? Unfortunately, in present day, there's not a lot of incentive for scientists who are professional scientists to go and attempt to reproduce these results, because you don't get any notoriety for showing something that's already been shown. You only get notoriety for discovering something that hasn't been discovered. However, the scientific method requires us to verify by performing repeated experiments the information that we come up with. We have to keep testing it. We have to keep validating it because of those possible problems that could crop up in our method. So consequently, this is a big issue in modern science. So we lack reproducibility. And so a lot of what we think is true is probably not. And so this is a caution for you as the next generation going in and becoming scientists and engineers, is to be more wary than your forefathers about reproducibility, and to really have a good understanding of what the scientific method requires.